Thank you. Okay, well, power series solutions. This gives us an optional way to find the solutions of some equations that you might recall. You studied these in calculus class. Look in the chapter on infinite series. So a power series is a function, f of x, that's the sum, n going from 0 to infinity, of c sub n times x minus a to the n power. So in other words, when n is 0, it's c0 times x minus a to the 0, so just c0. c1 times x minus a to the first, c2 times x minus a squared, blah, 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 blah. And the domain is the interval of convergence for this power series. And we've seen this before, because if you pick these c sub I as the Taylor series coefficients, this is just a Taylor series. So a power series is a Taylor series is a type of power series. So that shouldn't be all brand new.
Wow.
Right, so we've done that somewhere or other. So a function f is called analytic at a point A if it can be represented by a power series of x minus a, like centered at x equals a, with a positive radius of convergence. If it's not a positive radius of convergence, in other words, if the radius of convergence is 0, then it's not analytic. But we saw such functions, sine of x, cosine of x, e to the x, ln of x, in calculus class, represented by Taylor series and maybe even Maclaurin series for most of these. Taylor series for ln of x, because you have trouble with finding the derivative of ln of x, so you can't make the center be at x equals 1. So anyway, we used Taylor series in Unit 6, Lesson 4 as well. You might recall we set up some problems there, and so to find the interval convergence, we just force it to be absolute convergent by the ratio test, and see below we're going to do that. If it's absolutely convergent, then it's convergent. So the ratio test says here's a power series, and that converges for all values that make x, or for all values of x that make this limit L less than 1. And you might recognize this is like the n plus first term over the nth term. And if that limit is L and L is less than 1, then the power series converges for all those values of x that make that true. So find the interval of convergence for the given power series, and this is n going from 1 to infinity, x plus 7 to the n divided by square root of n. So we make the limit as n goes to infinity of the n plus first term, so that'd be x plus 7 to the n plus 1 divided by square root of n plus 1, over the nth term, which is x plus 7 to the n over square root of n. And if you put that together, notice that n of these will cancel out all n of these, so we just have 1 x plus 7. If we flip this over, this goes in the numerator, this goes in the denominator, we got the square root of n over n plus 1, which is 1. You can see that limit will go to 1 as n goes to infinity, I think, without too much difficulty. And we just need to make this less than 1. Well, for that we need absolute value of x plus 7 to be less than 1. So that leads us to x plus 7 is less than 1 and greater than negative 1. Now when we subtract 7 from both sides, we get negative 8 less than x less than negative 6, but we must check the endpoints. So if we put in x equals negative 6, then we got 1 to the n, so that's just 1, over the square root of n, and that's a divergent p series. P is equal to 1/2. Remember, it's only convergent if p is greater than 1. You understand why p equals 1/2? This is n, the square root of n is n to the 1/2 power. But if we put in negative 8, then we got a negative 1 numerator to the n power, and this is an alternating series. And to verify an alternating series convergence, we just need to know that the limit of the nth term is 0, and it is, and also show that this is decreasing for n greater than or equal to 1. So all we have to do is check the derivative of this to see if it's decreasing. So the derivative is negative 1/2 times 1 over x times the square root of x, or if you want to call it x to the negative 3 halves, that would work also. But that's going to be negative for all x that are positive integers, so the interval of convergence is from negative 8 to negative 6. Include the negative 8, because as we could see, on that interval, we have a convergent alternate series. So we include negative 8, but not negative 6, because then we have a divergent p series with p equal to positive a half. Okay, so note that arithmetic sequences or arithmetic operations like add, multiply, divide can be done with power series, and we already saw this when we looked at the series. Remember what a cool problem this was? E to the ix winds up being cosine of x plus I times the sine of x. I believe that was in our unit 2 somewhere along the way. And so, I'm sure we have a proof of that. So we'll look at a yucky example at the next video.